today's lecture, integral definitions and interpretations. We'll begin by defining the definite integral as the area under a curve. Then we'll talk about Riemann sums and define the definite integral as a limit. And then we'll talk about the fundamental theorem of calculus and compute definite integrals using this theorem. So we'll begin by the definite integral as assigned area. If f of x is a continuous function on an interval, closed interval, the definite integral between little a and little b of f of x dx is the signed area between the graph of y is equal to f of x and the x-axis. The definite integral is a number, while the indefinite integral, or antiderivative, is a family of functions. We saw that on Friday's lecture. Here's an example, the definite integral visualized. We have the graph of y is equal to x squared minus 1, and we look at what does it mean to take the definite integral of this function between -1 and 2 of x squared minus 1 dx. Well, that means the signed area under the curve from -1 to 2 of this function. In this case, the function lives below the x-axis from -1 to +1, and above the x-axis from +1 to +2. So it's equal to the area that's shaded purple, that's where the function lives above the x-axis, minus the area that's shaded green, that's where the function lives below the x-axis. So here, f and g are functions, and c is a constant, and we get some rules for the definite integral. The sum of the definite integral is the same. The definite integral of the sum of functions is the same as the sum of the definite integrals of those functions. Same thing for the difference. The definite integral of a difference of functions is the difference of the definite integrals. So you should notice a similarity between this. It's actually exactly the same thing. These are rules that carried over from the indefinite integral or antiderivative. And we'll see how they're actually related via the fundamental theorem of calculus. The definite integral from a to b of a constant times f of x, we can just call it the constant. We saw this also before with the indefinite integral. So the definite integral of a to b, a constant times f of x dx, is, we call it this constant, a constant times the definite integral from a to b of f of x times dx. Here's an example. If c is a positive constant, the definite integral from a to b, or it doesn't even have to be a constant, it could even be a negative constant, is any constant from a to b of f of x dx, then this definite integral is equal to c, the constant, times b minus a. Other example is to compute the definite integral from 0 to 2 of 3x dx by interpreting this definite integral as an area under a curve. And we'll see how that plays out in the next slide. So the graph of y is equal to 3x is a line, and 3x is larger than or equal to 0 if 0 is between x and 2. So this is the area we're computing. It's the area under the curve of y is equal to 3x from x equal to 0 to x equal to 2. The area of the curve is a triangle. It has base 2 and height 6. The area of a triangle with base b and height h is b times h divided by 2. So in this case, you're going to take b, which is 2, multiply by h, the height, and divide by 2. So you get 2 times 6, which is 12. Divide by 2, you get 6. The definite integral from 0 to 2 of 3x dx is equal to 6. There you have it. That's how you can actually compute a definite integral, just by interpreting it as the area under a curve. And it's actually possible to define a definite integral using what are called Riemann sums as a limit. Since the definite integral from a to b of f of x dx is a signed area, it can be approximated by signed areas of rectangles as follows. We have an interval from a to b. We divide into indirect subintervals of equal width, x0, x1. x0 is a, xj is a plus j times b minus a over n. J ranges from 1, or 0 in this case, to n. and each subinterval forms the width of a rectangle. Its width is equal to delta x, which is b minus a over n. Remember, these have equal width. So the length of the interval a to b has length b minus a, and we divide it into n subintervals, so they should have length b minus a divided by n. Select a value x of j star in x of j minus 1 to x of j, and evaluate f of x sub j star. F of x j star forms the height of the rectangle that's constructed over this interval. And the rectangle has area, height times width, which is f of x j star times delta x. We add up the area of n rectangles to get the Riemann sum. So what we're doing here is we have a subinterval that forms the width of a rectangle, and we choose a value in the subinterval and then look at the output of the function at that value that forms the height of the rectangle, or negative, or the height in this case could be negative, and we consider it a sine area, where that means, of course, the function lives below the x-axis. So its area, or signed area, really is height times width, which is f of x j star times delta x. Then you add up all these inner rectangles to get what's called a Riemann sum. F of x1 star times delta x plus f of x2 star times delta x plus f of x n star times delta x. Factor out delta x from each term, we get f of x1 star all the way through f of x n star delta x. This approximates, notice this is an approximation, the definite integral. Now, depending upon what we choose for xj star, if we choose it to just be xj, we get the right endpoint sum. If we choose it to be xj minus 1, we get the left endpoint sum. And these are important approximations. So you might have some homework problems or web assigned that's based off of this. Approximate the integral by the definite integral by using either right endpoint sums or left endpoint sums, Rn or, sorry, this should have been Ln. If it's xj plus xj minus 1 over 2, then the Riemann sum is a midpoint sum. So now this, you have to remember here, x1 star means x0 plus x1 over 2. Choose larger subdivisions as n goes to infinity. In this case, the length of subintervals goes to 0, and this Riemann sum, this sum of products, approaches the definite integral from a to b of f of x dx. Now we can actually define the limit at the definite integral of a function f of x from a to b as the limit as n goes to infinity of f of x1 star plus f of x2 star plus f of x n star times delta x. And if you notice, the definite integral is defined as a sum of products. When we defined the derivative, it was the limit of a quotient of differences. Quotients undo products, and differences undo sums, or vice versa. Products undo quotients, and sums undo differences. So it actually turns out that the derivative and the integral are, in a sense, inverse operations in a very special way. And that's what the Fundamental Theorem of Calculus says. We have capital F of x is an antiderivative of little f of x. Capital F prime of x is equal to little f of x. The Fundamental Theorem of Calculus states that the definite integral from a to b of f of x is equal to, just find an antiderivative, evaluate that antiderivative at the upper bound of the definite integral, and then subtract the value of the antiderivative at the lower bound of the definite integral. Any antiderivative, f of x, will give the same value of f of b minus f of a, so it doesn't matter. In that case, that usually means that you should ignore the constant of integration c. Here's a summary of the steps. To compute the definite integral of f of x from a to b, step 1, find an antiderivative. Step 2, evaluate the antiderivative at the upper bound and at the lower bound. Step 3, compute their difference. Here's an example. Let's find the net change in position when velocity is given. A rock is dropped from a building whose height is unknown. T seconds after the rock is dropped, its velocity is negative 32t, and its height is h of t, an unknown function. What is the net change in the height of the rock between t is 1 and t is 2? What is h of 2 minus h of 1? Since h prime of t is v of t, the definite integral from 1 to 2 of v of t dt is equal to the definite integral from 1 to 2 of negative 32t dt, which is h of 2 minus h of 1. That's the net change in height. So notice, even though h of t is an unknown function, we don't know how high this building is, or the height function. We do know whatever it is, its derivative is going to be the velocity function. So we know in particular that this definite integral is going to be equal to the net change in height. Now, to compute this, we follow the steps outlined in the previous slides. Step 1, find antiderivative of t. So notice we used the rules for definite integrals. We took out the negative 32t. Sorry, we took out the constant negative 32. And then antiderivative of t is just t squared over 2. Plug in f of 2 and f of 1, we get f of 2 is 2, f of 1 is a half. So compute the difference. F of 2 minus f of 1 is 3 halves. 2 minus 1 is 3 halves. And our conclusion is that the net change in height is negative 32 times 3 over 2. That's the same as negative 3 times 16, because negative 32 over 2 is 16, which is negative 48. So that means between the first second and the second, however high the rock was initially from being dropped, it had to fall a total of 48 feet between the first second and the second second. And that's regardless of how high it was dropped from. Actually, it depended. That's provided the velocity initially was 0. It was dropped, not thrown down. Okay, so that's it for today's lecture. I will see everyone on Wednesday, and then we'll go over more techniques of integration that will include the integration by parts as well as U substitution.